Hi again. So this is the second part, but I just want to cover a few more slides from the first deck. And again, you can find the slides on my website somewhere. So we talked about MCMC and gave some examples. I wanted to talk a little bit about Hamiltonian Monte Carlo, as this is an MCMC algorithm that's quite used in the statistical software available out there. Like PyMC in Python or Stan, which has interfaces in Python or R, or Julia. And so it works as follows. It's quite physics inspired, I guess, and it comes from physics, as most MCMC algorithms. So this one, the goal is to sample from the target distribution pi. And the state now is denoted by Q. And we think of it now as the position of a ball in a landscape described by the density pi. And we augment this position with a velocity, and that's denoted by P, or it could be a momentum, in fact, but I'm not a physicist, so one is mass times the other. And so this momentum, we draw it from a Gaussian distribution. Okay, so people talk about the potential energy for minus the log density of the target. The kinetic energy is 1/2 of the square norm of the momentum. And the total energy is the potential plus the kinetic energy. And so then you imagine that this mobile will move around the space with the conservation of total energy. Okay, so basically, as a way of moving around the state space to sample from pi, the idea is to imagine an actual physical object that would be like a frictionless ball, for example, going up and down the landscape described by pi. And so it would accelerate when it goes down, which corresponds to going to places of higher density, and it would decelerate when it goes back up. And there's no friction, right? So basically it would go up to the low region of densities, and then turn on itself, go back down. So there may be some trajectories shown somewhere later. Maybe I can do a little graph of what this may look like. So if we imagine the contour of a density in 2 dimensions, so those would be my target density. And we're trying to move around the state space. So again, as a reminder, yesterday we talked about Metropolis, Rosenbluth, Taylor, Hastings algorithms, where if we are at a given point, we could propose, according to, for example, a random walk around the current points, and accept or not the proposed points based on this ratio of target densities at the proposed and the current points. But here the idea is a bit more sophisticated. We're drawing a velocity. So from a Gaussian, right? So for example, we draw this vector here. So it's a Gaussian of the same dimension as the original problem. So if we have a 2-dimensional density, we have a 2-dimensional velocity. And so we go there, and then we solve the equation of motion, basically the Hamiltonian dynamics equation. And so here we're going uphill a bit in the beginning. So we're going to turn back to a region where we go down. Maybe we're going to traverse here and go here and then turn back on ourselves. Right. Maybe. Right. So I'm trying to draw the trajectory of a mobile that would start with this initial velocity. And so you do that for a little while, and then you stop, and then you draw a new velocity, afresh, and you solve the equations again, and you stop, and it gives you a bunch of points. Or if you can do that exactly, that would give you points that would, again, satisfy a detailed balance and leave the target distribution invariant. It would be a valid way of doing MCMC. So in fact, we can't typically solve those equations. So they are deterministic system of equations, but they're not linear, and in general, you can't solve them exactly. But what you can do is discretize. So that's... The initial normal is the component P of the dynamics. And so the E energy depends on the position and the velocity. So E is basically minus the log of the density of this extended target pi bar that I'm writing here. And what you're going to do is sample from pi bar and just keep the positions. And this dynamics is the Hamiltonian equations. So that sort of describe the trajectory of this mobile that conserves total energy. Okay? Yep.
So if I understand correctly, the way in which this is different from Carlo's Miller Hastings algorithm is the way in which we propose how we move around the state space.
Right.
There we were just proposing from some Q. Here we're proposing from something that I guess is written down as a distribution, but can be written down as a distribution that's inspired by.
Yeah, actually, you could see this as a particular case with a fancy proposal Q, and the fact that we went from the original state space to an extended state space, so we doubled the dimension. But it is still, I mean, Metropolis Hastings encapsulates nearly everything, in fact. So this is kind of a fancy proposal mechanism. So it's only applicable if your state space is continuous, and as you can suspect, it's going to work well when the target is quite smooth, when the density is quite smooth, and then the gradient gives you a lot of information about where to go. But if you have discrete components, then this does not apply, for example. So then there's a discretization of it. So just to note that it is not a simple forward Euler scheme. That would not work well at all. This is a more fancy integrator with a sort of a midpoint. So, I mean, it's not very complicated to implement. You only need to be able to evaluate the gradient of the log density. That's this u or minus u function. The gradient is a gradient of u. And at the end of the day, you have an acceptance rate, which is quite reminiscent, as you can see from the Metropolis Hastings. Somehow the proposal disappears as well, because if you arrive at a certain point and then you flip the velocity, so you have at this point with this velocity, if you flip the velocity and you solve the equations again for the same amount of time, you will go back exactly to the original place. And so there's a way of justifying that there's no proposal distributions appearing in the ratio. They cancel out. Okay. And actually, when you look at this discretization, there's a certain number of steps and a step size eta. If you were to do only one step, this would basically amount to just following the gradients and then adding some noise. So you can work it out. And so then it's exactly equivalent to the Langevin discrete proposal that we've seen yesterday. Okay? It's a fancy version of following the gradient and adding some noise. So it's been studied a lot. It works really well for like multivariate Gaussian distributions or distributions that are not too far from that. And in those cases, you can show that the convergence of the chain is practically independent of the dimension. So that's the big appeal. In certain classes of Bayesian inference problems where the posterior distribution is quite close to being a Gaussian anyway, and this is very popular. Yeah.
So it seems like the intuition behind the dynamics is to, as you pointed out, spend more time in areas where there's high density, spend less time in areas of low density.
Mm-hmm.
I can imagine writing other dynamics, like other formulas that take us on a path where we do spend more time in high density, less time in low density, that are different from these physically inspired blocks. Have people explored other possible dynamics, and is there maybe a reason why, like the way that nature does things? I don't know. Maybe that's like a question.
Yeah, there's a lot of appeal to nature, which are, moderately convincing. I mean, there's a lot of different algorithms, but I'm sure there's plenty more to explore. Yeah, if you have something specific in mind,
I mean, one thing I thought of was if you were to look at the potential energy equation, it was negative log pi L.
Yeah.
What was it? Right, negative log pi Q.
Mm-hmm.
And it made me wonder, if you were to tell me the intuition, I would have thought the
Right. Yeah. Yeah, that's a good point. I mean, I'm sure you can do it with minus pi. In fact, you can solve the equations for a potential that is not your target potential. So you can imagine if it's expensive to compute the gradient for your target, you can have any approximation or even a potential that would make you go to particular places. You can plug that in. And as long as you correct with the right targets in the acceptance ratio, that works out. Because this is just a way of coming up with a proposal. And so, in fact, you could also play with the kinetic energy. So people have been doing that quite a bit. Replace this Gaussian velocity by, for example, heavy-tailed velocity, so that sometimes you try to go really far away. There's a paper that explains that there's no reason why this would be better than random walk metropolis Hastings when the target has multiple modes that are well separated. So this doesn't really solve the multimodal problem. This solves more like a sort of, and it's not obvious from this description, but it behaves well in high dimension for Gaussian-like distributions, I would say. So they tend to arise a lot in sort of classical Bayesian hierarchical models. But it has to be classical. So for example, even in regression settings, well, the theory, the sort of Bayesian theory guides towards priors that are so-called shrinkage priors, like horseshoe priors that are sort of heavy-tailed. Then actually this algorithm doesn't work in that case. So it's very popular, but it really is super efficient in quite a specific class of models. But then it turns out that in sort of Bayesian political science, for example, everyone used the same type of hierarchical models for which this works really well. And so then there's a lot of users of those packages that implement these methods. But I think it doesn't represent the fact that there's all sorts of targets and problems that could not be solved well with this. Of course, there are some questions about tuning parameters and so on. But I just wanted to mention this because this is one of the most sort of popular algorithms at the moment. Okay, and then I'm going to move on to, so here are a few references for this algorithm, which dates back to 1987 in the physics literature. It was hugely popularized by Radford Neal in machine learning and statistics. And there's this paper that shows that in a sort of stylized example, it doesn't work better than random walk metropolis Hastings when the modes are well separated. And this is a connection with yet another optimization method. So there are optimization methods that also operate a bit like this, called momentum methods. And so there's this paper in particular that makes very strong, nearly one-to-one connection between those optimization methods and sampling methods. Okay, I'm going to move on to slides du jour here. Okay, so today, I'm going to talk again about this probit regression example, which I sort of briefly described yesterday, to give yet another example of an MCMC algorithm, and then we go into more theoretical topics. And then tomorrow and Thursday, we'll go back to more methodology. Okay. So it's kind of methodology that will be inspired by those theoretical devices that I'm going to present today. In particular, the idea of couplings of Markov chains in particular, and the so-called Poisson equation. Okay, so just a checkpoint for, just so that we're on the same page in terms of the notation. Trying to sample from a target distribution pi. And we start a Markov chain from pi 0, and then we iteratively generate the next xt, given xt minus 1. And we denote by p the so-called Markov transition or Markov transition kernel, which is just a conditional distribution given or indexed, if you want, by the point xt minus 1. So we're trying to estimate some integrals with respect to pi. We denote by pi sub t the marginal distribution after t steps. So pi sub 1, for example, is what happens when you start from pi 0 and you do one step. And this can be written as an integral pi 0 dx, px dx prime. This notation pi 0 p It's kind of an operator notation that takes a measure on the left and returns a measure. It's actually intuitive in the sense that if you were in a discrete state space setting, a finite state space setting, well, so the transition would be described by a matrix which each row would describe the probabilities of where you can go depending on where you are. So where you are would index the row. And the vector of probabilities, pi 0, would be just describing where you start. And so then pi 0p would literally be a row vector times a matrix multiplication. Would give you back a new row vector, and that would be pi 1. So this notation is intuitive in that sense. It's just, here we're not thinking specifically of finite state spaces. Okay, and conditional expectation, so ph, so the same p, the transition. If you put a function on the right, it returns a function, so it's also an operator. It's also the case here that if you would put a vector on the right, you would get back a vector, and you would have the meaning that you want in the finite state space setting. And here it's basically the conditional expectation after one step. So if you were to start a chain at little x, and you do one step, apply the function h, you take the expectation of that given where you started, that's denoted by ph of x. Okay? This is shorter than to write expectation of h of x1 given x0 equal x, but it's the same thing. Okay, so back to the probit regression example, and then tomorrow I'll try to put a quantile regression, a Bayesian quantile regression example. Here we have this binary outcome. We have some covariates, and we're trying to do regression with the probit regression. And as we discussed yesterday, it's equivalent to introducing latent variable z that would simply be Gaussian with center x beta, and noise variance equal to 1. And then to say that yi is 1 if z is positive and 0 if z is negative. So if you put a prior distribution, like a normal distribution in particular, it's going to play nicely. Because then you can work out the conditional distribution of each z given beta, and that's a truncated Gaussian. So depending on whether the corresponding outcome is equal to 1 or 0, it's truncated on the left. See yi is equal to 1, that means that zi must be more than 0, so it's truncated on the left by 0. And if yi is equal to 0, then it's truncated on the right, because it means that zi must be negative. Okay, so that's the conditional distribution of one of those z's given beta, and of course given the data, yx. So here I hope it's not too confusing. Usually I call x the Markov chain, but in just this slide for the probit regression, x is the covariate in the probit regression. And then beta given z, so you can work out that if you have z, you can forget temporarily about y, because in this model, beta only appears in the equation where there's a z. So if you condition on z, it looks just like a linear regression problem with Gaussian noise. And so that's why if you put a Gaussian prior, you have this so-called conjugacy, where you obtain a Gaussian posterior. So that's a game of completing the square if you want to write the prior times the likelihood, right? So you have product of two multivariate Gaussian densities. You can collect that, and that's a multivariate Gaussian density. Okay, so this algorithm works as follows. So it's still an MCMC algorithm because it's creating a Markov chain. And it works by alternatively sampling from the conditional distributions. So that's another case, another particular case of metropolis Hastings, in fact. So if your proposal is exactly the conditional distribution of some components given other components of pi, and you work out the acceptance rate in the metropolis algorithm, you find that the acceptance will be equal to 1. Okay? So it's like there's a proposal that's always accepted, and that proposal is from the conditional distribution. So it is still a particular case of what we've seen before. Okay, so here you have lots of, it's a high-dimensional Markov chain because we've introduced one z for each row of the data. Right? And then there's one beta for each of the columns, and that's the problem of interest, so that's normal, but it could be that in some cases when n is large, we really end up with a large dimensional chain, even though we're interested in perhaps a smaller dimensional object. Yes?
So you just mentioned that this sort of alternatively proposing from these conditional distributions is an example of MCMC
Metropolis.
pacing.
Yeah.
I think we also talked about Gibbs sampling.
Right.
And is this an example of a Gibbs sampling?
Yeah, absolutely. Yeah, this is an example of Gibbs sampling where you update. Gibbs sampling, it's quite ill-defined, all of this, the terminology. Because again, the original paper by Metropolis et al. That was doing that was updating certain components with a proposal that would be accepted or not. So some people now would call it Metropolis within Gibbs. And Gibbs would be when you exactly sample from the conditionals, like here. But again, like if you exactly sample from the conditionals, it's like a certain choice of proposal. So there's not a real difference between Gibbs and Metropolis within Gibbs. So that clarifies. The terminology is a bit strange. There's a bit of a zoo of MCMC algorithms developed by multiple communities. Like the Hamiltonian Monte Carlo algorithm is also called the hybrid Monte Carlo algorithm for some reason. So yeah.
Can I ask you just one simple question about the equation for data element vector of the z's?
Yeah.
So why? I mean, because that's really just the standard formula for Bayesian updating if there were no constraint on the size of the
Yeah.
CIs, right?
Right.
But why is it the case that this information about the signs of the ZIs, the truncation, doesn't affect that update formula?
Yeah, it's only coming in the Z update and not in the beta update. So it is coming in. Huh? The Ys play a role, of course.
That information is contained the ZI.
Yeah. But it turns out that it's like if you write the whole likelihood.
That indicator is not going to mess up my posterior, the indicator that the ZI needs to be positive if I know that the corresponding YI is.
But if you condition on the Zs, again, like the model, beta only appears in this part of the model. Right? So if you condition on the Z, you can sort of temporarily forget about the Ys, as it happens. You can do a graph of the variables and their dependencies and, you know. Okay, so I have an example where I ran the algorithm. There was 10 covariates and 12,000 data points, rows. I'll give the reference maybe tomorrow because I forgot to put it in the slides. And this is a trace plot of the 10 components of beta. Okay? Actually, you know, I don't start at 0 here. Something crazy happened at 0. All the components go out and then back for some reason. So in order to have a readable plot, I truncated. I start from the origin, but the algorithm is such that the components go wild and then come back. And then it looks like this, okay? And so you can see that there are serial correlations, and it's not IID samples. Okay? And you can see that maybe it's stabilizing. So hopefully we're reaching stationarity, we're reaching pi. So maybe it's enough to do 100 steps and take the last draw, but we don't know, right? So if people would see that in MCMC, they would run a lot more iterations. They would wait until the trace plot looked very, very stable, like sort of caterpillars looking trace plots. They don't like things that are transient. Right? Okay? So the big question, in a sense, we're going to try to address tomorrow and after tomorrow is how long we should run this. Today, we'll try to assess this more theoretically. This is some of the Zs also that are looking like maybe they're stabilizing after 100 steps. This is just the first 10 Zs, but there are 12,000 of them. So it's hard to look at all of them. Okay, so some of the questions we'll be looking at, convergence of the marginals. So pi t, the marginal distribution at step t. If everything goes well, it should be going towards pi. We're going to give some conditions in a minute. So the distance, in some sense, so those are two distributions. We need to define a distance. It could be total variation. It could be optimal transport distances. It could be Kullback-Leibler divergences. Right, so usually people choose whatever is convenient for the proof that comes next. So that's the main the main reason to choose a distance is the convenience for the proofs. But you could be interested in more directly relevant convergences in terms of what you're actually estimating. So if you want to estimate the probability that your first regression coefficient is positive, you're going to take the test function h that maps the whole z and beta to the indicator that the first component of the beta is positive. And then you're going to have basically zeros and ones here along the chain. And you take the average, it's going to go to a certain probability. And under weak conditions, there's a guarantee that in the limit of the number of iterations, this will go towards your quantity of interest. Furthermore, the estimates in MCMC typically satisfy a central limit theorem. We're going to see again some conditions for that. So that says that the convergence rate is square root of the effort, the computational cost, which is linear in the number of steps. And the deviations are Gaussian with an asymptotic variance that we'll discuss a bit today in connection with the Poisson equation. But it's not IID, right? So if it was IID, the asymptotic variance would be the variance of h of x under pi. But here it's not. There are correlations, so it's a more complicated object. It's complicated to estimate. However, the rate of convergence in terms of t, it would be the same. Right? If you did t draws of IID, you'd still have a convergence rate square root of t, just the variance would be different. Note also, this works in any dimension, right? So there may be some dependency on the variance hidden in the asymptotic variance, but as rate of convergence, it's always square root of number of points in all dimensions. Right? So that's intuitively that's why Monte Carlo works well in high dimension, is that there's always the same convergence rate. But it's it could be very misleading because I could be hiding horrible stuff in the asymptotic variance. Okay? Yeah.
Sorry, are these questions or results? Questions we're going to be answering next.
Yeah, the good point. So the question would be, ultimately the question is for our probit regression MCMC, how long should we run it? How long should we run it for what to happen? So either for the marginal distribution to be nearly pi, because you want to take the last draws and take them as samples from the target, or maybe you want to run it for as long as it takes for your estimate to be close to your quantity of interest. And this would be more closely related to the central limit theorem. But the question then would be, first, are you in the asymptotic regime? And so is that a good approximation of that? And secondly, what is the variance? It's not given to you a priori. So the question here is very implicit in the slide, I agree, would be what is the variance in there? Yeah.
Considering the first point, we want to take the last n draws as the representative, as the draws from the pi, right?
Possibly, yeah. Again, in the spirit of maybe parallel computation.
Parallel and then one draw.
Yeah, and again, you could take the last. So you don't want to average over all the draws, right? If you see a trace like this, intuitively, if you want to estimate something, you want to discard the transient part in the beginning. That's called the warm-up phase or burn-in MCMC. So you want to discard the burn-in. But you do want to not take the last, but the last few. But I'm simplifying and saying, if you knew that 100 steps was enough, and you had a lot of parallel machines, you would run a lot of chains for 100 steps. And maybe you'll take the last 10 or the last 20. And again, it's quite crucial if you're a bit pessimistic about the perspective of much faster computers in the next 10, 20 years, but you have more and more data, you want to try more and more complicated models, you want to try quantile regression instead of linear regression, and everything comes with a cost. And if you can't rely on just machines getting faster, and well, maybe ChatGPT helps in optimizing the code a little bit, and there may be some gains there, but it would be really good to be able to leverage parallel machines. Because that's already there. Like you can go, it costs money, but you put your credit card on some services online and you can rent 1,000 machines. It's not that expensive. It's quite accessible. If you rent 1,000 machines for an hour, you can afford most labs, even in developing countries, can afford that. It's quite cheap. And so that would be nice if we had computational methods that could take advantage of that. Even there are more experimental concepts of distributed computing, where, for example, if we take all the smartphones in this room, we have a lot of computing power, right? So if I put online a service where basically a URL I share with you, you just have to connect to the URL, and that's called volunteer computing. You just put a URL, and your machine starts working. So of course your battery would drain, and you would complain, but there are plugs. Ultimately, the University of Chicago would be paying the bill, I guess, in this case. And we could have like probably 100 or 500 cores here right now, right? If it was just one URL away. So that's my personal objective would be to develop like a service like this, but that really requires computation that are very distributed in nature. Right, so on the other hand, if we're trying to do a very long chain, it's not easy, right? I mean, we need the result of step T in order to start working on step T plus 1, so if we have 500 cores, what do we do? Okay, so some basic results about convergence of Markov chains. So in MCMC, if you take a general book on Markov chains, there could be lots of situations where we'll never be in MCMC. So we are sort of in an easy scenario, because by design we construct chains for them to converge to the specific target that we're interested in. And so, for example, by design, if you can check detailed balance like we did yesterday, the chain will be pi invariant, so it will have an invariant distribution. It's not enough for convergence because, for example, if your transition is a Dirac mass at the current state, then you will not converge to pi. Even though if you were already at pi, you would stay there. But it turns out that irreducibility, aperiodicity, and pi invariance imply convergence. So irreducibility, I can write down the definition. It means that for all states X and measurable set A, it should be for pi almost all X and pi measurable A's. There exists a T, a time, such that there's a probability of entering A from X. But it doesn't have to be the same time for all X's and A. So it's quite a mild condition. It means you can go everywhere where pi puts some mass. If you can't, then it looks bad. There's going to be a problem. So for example, if your target distribution had a mode like this, and then zero mass, and then a mode like this, so like a sum of two uniforms, mixture of uniforms, and if your proposal is to do a uniform move in a small ball around where you are, then there's no way you can access the other mode from one, so the chain is not irreducible. But for example, if you are in R to the power D, technically, if you do any sort of Gaussian proposal, it would put mass a little bit everywhere, and then your chain is irreducible. So it clearly doesn't mean it's going to work well, but the condition is satisfied. Okay, so that's irreducibility. And aperiodicity is the fact that you cannot partition the state space in such a way that the chain moves deterministically from one set to another set of the partition. Otherwise, it would be periodic. Okay. So it's not like at the all odd iterations, you're in the positive part of the space, and in even iterations, you're in the negatives, that would be periodic. So for any chain that has a possibility of staying where it is at the moment, so when there is a rejection probability, then it cannot be periodic. Because the fact that you can stay with some probability where you are will break the periodicity. So this will also not be a problem for MCMC. Okay, so basically in many, many settings, there's no doubt that there is convergence. And it's not indicative of good performance. It's just formally there is a certain time at which pi t would be close to pi. The law of large number also is incredibly general. So if h has a finite moment under pi, which is what you would need for the law of large number for IID samples. So, it's not surprising that you need it also when you don't have IID sample, but you don't need anything else. If you have this condition plus finite moment, then you have a law of large number. So there's nothing, no added price for having a Markov chain. I mean, again, this is under those conditions. So Main in 3D is a reference book on all those properties of Markov chains. And next, we're going to talk about the central limit theorem. So the central limit theorem is more sophisticated because now the variance, the asymptotic variance on the right-hand side, of course, it depends on P, the transition. So if you change the algorithm, you'll not have the same asymptotic variance. And as a back-of-the-envelope calculation, if you want to have an expression of it, what you can do is take the variance of the average. So variance of a sum, you can expand it as a double sum of covariances, right? And so here, there's a 1 over t, and you take a limit, and you can write the asymptotic variance as an infinite sum, basically. So it's still kind of a double sum, but we simplified it because this is a Markov chain, it's the same covariance between x0 and x1 and between x1 and x2 at stationarity. So those stars here mean we're talking about at stationarity because it's an asymptotic quantity and asymptotically we are at stationarity. Okay, so this is the asymptotic variance and you can see that it's not going to be super nice to estimate. You may be familiar with such problems as well, maybe in econometrics.
Long-run variance.
Long-run variance, yeah, exactly. 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 So there's a lot of estimates, hack type estimators, and they all are useful in MCMC. Yeah. So this is a long-run variance. And why is it complicated to estimate? Is because first you have infinitely many terms, right? So that looks tricky to estimate. So the most naive thing that you can do is from a long run, you can just decide that you're going to truncate the sum and compute just a certain number of covariances and drop the others. So you're going to be biased. A less naive thing to do would be to truncate the sum, but then reweight the terms so that you're asymptotically unbiased. That's like half of the estimates out there are based on different choices of covariances. So you replace the covariance by an empirical covariance, you truncate the sum, and you reweight the terms to be as close as possible to the limit, essentially. There are other ways of looking at it, but it's considered pretty tricky to estimate. In MCMC, it's useful because, in a sense, the difference between a good and a bad MCMC algorithm is one way of capturing what's going on is really to compare the asymptotic variances. You want a small asymptotic variance. So it's useful, although people sometimes express things differently in MCMC. They talk about effective sample sizes, which is really just in one-to-one bijection with asymptotic variances. But it's just the number of samples divided by 1 plus the variance, I think. And it's supposed to be, or just divided by the variance. Divided by the variance, but rescaled so that you have a number that would be representing the number of IID samples that would lead you to having the same variance in your estimate as this. So it's called the effective sample size. So like the sample size of an IID sample that would lead you to the same type of error. So when people talk about effective sample size, which is everywhere in MCMC, they need, in order to estimate that, they need to estimate the asymptotic variance. Okay, so we're going to talk about how to prove the CLT a little bit using the so-called Poisson equation. So recall this notation. PH is this conditional expectation after one step. And we say that a function g is solution of the Poisson equation if the function g minus pg is equal to the function h minus pi of h. So you give yourself a test function h. This is a centering, right? You divide by, you subtract the target expectation. And g is solution if g minus the conditional expectation of g after one step is equal everywhere. So equality between function here has to be equal everywhere to that function. So in order to save time, instead of saying g is the solution of the Poisson equation, I'll say that g is fishy, because Poisson means fish in France. So it's named after Denis Poisson. And a lot of things are called the Poisson equation, as it turns out. Every field of applied math or math has a Poisson equation. But in context of Markov chain, usually it's that one. Okay, so they're not unique first, the solutions, because if you add a constant to G, the same constant will be in PG. Yeah, because it's a linear operator, it's an integral. So the constant would be going out of the integral. So G minus PG is the same if you add any number to G. Okay. So if there is a solution, there's many solutions. There is a solution under this condition. Okay, so it looks a bit complicated. So there's an infinite sum of conditional expectations after t steps. So p to the t is the transition in t steps of this centered function h and in L1 pi norm. Okay. So that means basically that this must go to 0 fast enough. So why would it go to 0? So this is the target expectation. And this is the conditional expectation when you do t steps of MCMC, starting from a specific x, but if t is large, it doesn't matter anymore where you started t steps before. And so the conditional expectation will get closer to the target expectation. So the difference would go to 0 if all goes well. And if it goes, for example, geometrically, then it's summable. If it goes polynomially, then it depends on the order of the polynomial. Yeah.
So just to read the main display correctly, so it implicitly depends on some little x, so it's G the mean by the conditional expectation afterwards is the same as H the mean.
Yeah, it's, let me write it with x's, and it will be useful. I'm saying that for all x, this holds. Again, it's probably only necessary for pi almost all x. It looks weird, but we'll see how convenient it is in one slide, and maybe it was introduced to serve a specific purpose. And you'll see, and that purpose is to prove the CLT for Markov chain ergodic averages.
So it gives you an H and you're looking for a G that.
Yes, you're right. So the input of this indeed is P and H. And pi is kind of implied by P because P is pi invariant. So the input is this, and what you're looking for is a G.
I'm giving you an H, I'm going to diminish it this way, and I'm telling you if I'm diminishing with a slightly different expectation, what's the G that gets this equality?
Yes.
And that, okay.
Like why would we care about this, right?
Yeah.
So let's see. So first, just to give a concrete solution of this problem. So this horrible function at the top is fishy. So it's very easy to prove that it's fishy once you have it, right? So G is this. PG, what is it? So P times this. You put the P inside the sum. We're doing things with our hands here, right? Everything is possible. Everything is allowed. So we put P inside. So P to the T becomes P to the T plus 1. Right? So that means that if we do G minus PG, we have a sum that starts at 0 minus a sum which we can reparameterize to start at 1. And we're left with only the very first term corresponding to T equals 0. And so for T equals 0, P to the 0 is like doing 0 steps, so it's the identity. And we're left with H minus pi of H. Right? So at least if we are given this form of a solution, then we can check that it is a solution. Okay. So it remains fishy if you add any constant to it. What is less obvious, but true under the assumption that this is in L1 of pi, is that all the solutions are equal to this one plus a constant. That's not so obvious. Yeah, so in LaTeX you can go crazy. Huh? There's multiple packages, probably for linguists. So this is in a hieroglyph package. Yeah.
And this exists because of our condition in the previous slide.
Yes, exactly.
What is the subscript L1?
So this is in the L1 norm, so that means you want a function, if you have a function f, This means that this is finite. This is, sorry, the one norm is this. The LP norm of pi is this. F of x. Okay, so why do we care about this? So suppose you want to prove the CLT. So you're looking at the, well, just up to 1 over t, this is my average. I'm trying to show that this goes to a Gaussian, okay, up to the square root of t scaling. But if I assume that there is a Fichy function, instead of h minus pi of h, I can write g minus pg. But here I did a trick. On top of writing g minus pg for every xs, I also introduced a little lag. So I removed the last term and added the first term. So I have a one-time difference here. Okay. So this is assuming there's a Fichy function and doing this trick. And then the next thing is that conditionally on xs minus 1, the expectation of this is exactly equal to this. Right? Conditionally on xs minus 1, the expectation of g of xs is, by definition, pg of xs minus 1. So that means that this is a martingale difference sequence. So they're uncorrelated. And so, well, so it's still not IID, but it's much easier to have a CLT for martingale difference sequences. And so here you obtain basically a CLT for Markov chain averages from any CLT on martingale difference sequences. And on top of that, it will give you the form of the asymptotic variance, because this is your martingale difference sequence. And so at stationarity, this is the asymptotic variance, the second moment of it, the first moment being 0. Yeah? So now you have an asymptotic variance here, which looks a bit different from the one we've seen before. I would say more familiar one. Right? This is the asymptotic variance, infinite sum of covariances. And now we're saying it's also equal to this. It must be the same thing if those two things exist.
Then going back to like where did this come from? So someone sat in their living room, said, "What do we have CLTs for?" Well, for martingale.
Yeah.
And so we need somehow to limit with this conditional expectation. So we energy is going to do it, and then turns out.
I imagine. Yeah. Yes. Yeah, that's exactly it. It's quite smart.
Yeah.
I've tried to find the first reference, and I know there's this Marie Duflo, but she passed away a few years ago, so I never met her. So I don't know what she thought about. But this is a book which has never been translated, but that contains exactly this reasoning. And now, so this is a quite modern book on Markov chains with a view towards MCMC. Very good book. There's a whole chapter on this Poisson equation. Okay, so we can reconcile the two expressions. So we had this sort of infinite sum of covariances, more familiar long-run variance expression. And the martingale difference sequence reasoning gives us this expression. But recall that G itself has an infinite sum in it. Right? I mean, this particular G. And so, in fact, with some rewriting, you can reconcile that the two expressions are exactly the same. It takes a little bit of tedious calculations, so I'm not going to do it. Okay, it's been known also that the Poisson equation can be interpreted as something to do with the bias of Markov chains. And again, we're quite interested in the bias because it's the thing that prevents us from using parallel machines. If they were unbiased, we could just run them in parallel and average. So if you look at the average, the ergodic average, its expectation, if you want to look at the bias, you want to look at its expectation compared to the expectation of interest. So its expectation you can write exactly in terms of p to the sh, right? We did the expectation of the s term conditionally on where the chain starts. So let's call it a little x0. So the conditional expectation of the ergodic average given the starting point is this. And so then if you do the bias, which is this, but remultiplied by t, and you realize that the conditional expectation here is exactly this p to the s, you find in fact that this g function exactly is the bias. Okay, so this G function that was useful for proving the CLT. In fact, if you evaluate it at any little x, it tells you the bias of the ergodic average, the asymptotic bias. And so the bias will be of order 1 over t in passing. Also, you can see it from here. So if you multiply by t, you call this asymptotic bias, you see how it would vary based on the starting point. So now you can imagine that, for example, it will tend to be very large when the starting point is very far away from the mode. That tells you a little bit about what this G function may look like. Okay. So that has been noticed for a while, and then there's various variance reduction tricks that are in the literature, for example, by those authors, based on the Poisson equation. Okay, so I'll just put that here, okay, just to provide a little bit of justification for the CLT, but also tomorrow we go back to playing a bit with the Poisson equation, but with a more methodological viewpoint, trying to come up with a new method.
But just to get a sense of the theorem, so the theorem is like, so I start with a pi and with some transition kernel, and then, so the theorem says, if pi and the transition kernel, if there's a Fishy function for them, then you have the central limit theorem with the long covariance, so that's the theorem?
Yeah.
And so, what are a little bit more, are there more, let me call it primitive conditions on just pi and the transition kernel, or, because what do I start with? I don't even start with pi, I start with something that is proportional to pi or something. So I start with anything proportional to pi, and I create the transition kernel by using whatever trick I want. And then
That's true, yeah.
I need to verify something on them so that I can invoke this theorem.
Yeah, absolutely. You're right. So if you take an MCMC algorithm and target a real problem you have in stats or econometrics, how can you check that this holds? Okay, so it goes through a bunch of steps. So for example, if you use a random walk type of proposal and your target distribution has tails of a certain way, the problem usually is in the tails. Yeah. So with a random walk, you're going to eventually visit the middle part as you should. The problem is what happens in the tails. So for example, if you have very heavy tails, but your proposal is light tailed, this may not hold. So and you can really see it when you run a random walk Rosenbluth algorithm on a Cauchy target, and your random walk are Gaussian. It would look like it would drift, basically. It doesn't go back to the center. But if you use Cauchy proposals, well, it's a very contrived example, but if you use Cauchy proposal on a Cauchy target, it works. So there are conditions on the target that you can verify sometimes. Because, for example, in Bayesian inference, the rate of decay of the targets are quite explicit. I mean, you have a prior, you can look at it. Usually the prior actually regularizes a lot. Yeah. So for example, if you have a separated logistic regression likelihood, there would be a problem. But if you put a Gaussian prior on the coefficients, then there's no problem. So then, for example, for logistic regression, you can check that the distribution is log concave. And it can be even strongly log concave depending on conditions on the matrices. And so then you can really apply those theorems, but it's kind of a case by case. Right.
T, then something shows up.
Right.
And that something is the Fishy function associated
Right.
with it.
Yeah, exactly. You're right. So in a sense, the bias. Why am I making a big deal out of this bias, which is negligible compared to the variance? You could say that because the variance is of order 1 over t, but the bias square is of order 1 over t square. So it's asymptotically negligible. But then when you look at the traces, you get the feeling that if you do too few steps, there's going to be a very significant problem, right? And that's the bias. So the fact that it's of an asymptotically negligible order compared to the variance is true, it's a fact, but doesn't mean it's not a real problem when you're trying to do short chains in order to leverage, in particular, parallel computation. But also because you have to stop somewhere anyway. You're doing, you don't even know if the number of iterations you're doing is big or not. Like that would require knowing how many you should be doing. And I guess, if it was the case that in all problems 1,000 is enough, then we can just do 1,000 every time. Right? But the problem is if you look at the literature, so the original paper in 1953 does 60 steps. And a few years ago, there was a paper in the political science literature on redistricting, gerrymandering. They do very sophisticated MCMC algorithms in order to sample redistricting plans, in order to try to do a hypothesis test to see if there was some sort of how dodgy the redistricting was, basically. And then there's a paper that mentions the run of 1 trillion iterations. And 1 trillion is 10 to the 12. So some people run things for a long time, like months on a big computer. And so that's because of the bias, in my view. Because if there was no bias, then they would do lots of shorter chains.
I'm a bit confused by the results for the bias. The result doesn't distinguish if you have many parallel chains and if you have samples from a unique chain, right?
Yeah, here, all this in writing in the slides is about one chain, going for t steps, and looking at the asymptotic when t goes to infinity.
Yes, so you don't have, you have the same bias whether it's a single chain.
Yeah, exactly.
But you emphasize the problem of parallelism, which but it's not really a parallel issue.
No, yeah, okay. So what I have in mind is that if you have lots of independent copies of any of those estimates, and you average, the variance is going to get reduced to 0, but not the bias. Right? So that's what I have in mind. Yeah.
And that's true also if you start at different starting points and you get different biases, but they still don't have 0.
Yeah, but if you knew how to combine biases in such a way that you cancel them out, you're actually getting at some of the methods we'll see tomorrow to try to get rid of that bias. In fact, in some way, we're going to start indeed pairs of chains at different points and do some sort of telescopic sum magic to get rid of the bias. It's true to keep in mind that the variance goes down with parallel replicates and not the bias. Okay. So I want to move on a bit to also the concept of couplings and just one proof of convergence of the marginals, so pi t going to pi. I'll mention another proof for the Langevin diffusion, and that will be it for today. Okay, so first, let me be a bit more specific than before about the distances that we're going to use and the type of result that we want to get. So we said convergence of the marginal is something like this. Now I'm going to be more specifically talking about the total variation distance and the one Wasserstein distance for the distance. So here the distance between two, I'm writing this as a norm. This is distance between two distributions. And instead of writing going to 0, I would like to have a rate if possible. So I would like to have an upper bound. Well, if I could have an equality, I would be even happier, but I'll be okay with an upper bound. That would be a function of t that goes to 0. And it's quite interesting for people in MCMC to know the rate of convergence. So for example, if the upper bound is c rho to the power t for some constant c and some rho in 0, 1, that then means this function goes down geometrically and the rate is, rho is called the rate of convergence. Right? So rho may depend on the dimension of the problem, the number of points in your data set, the number of covariates if you're doing regression, and so on. And recently, there's been quite a lot of papers trying to get really quite quantitative about what rho may involve, how it scales with the dimension, for example. I'll mention in a table some recent results, but they are pretty hard to prove. I mean, it would have taken probably 4 times an hour and a half to do a solid proof of of a result like this.
And what do you mean is that the C and the say rho in the geometric ergodicity, they depend on pi, right? Like
Yes.
thinking about like doing uniform results over some classes of pi's where
That's a good point. Yeah, usually, at the moment, it's for a very specific fixed pi.
fixed pi. Perfect. Okay.
But as we discussed yesterday, of course, it's interesting to wonder about, because pi, say it's the posterior distribution or the distribution of a test statistic or something, it could be random itself. Or it could come from it could have been generated. For example, a posterior distribution, it's a fixed quantity if you fix the data, but you may want to know how it moves around if you resample the data. And so then, indeed, it would be interesting to have results that take that into account. And there are very few in my, to the best of my knowledge. There's starting to be some. Okay, so geometric ergodicity, and then there's polynomial ergodicity. So that's when the convergence is polynomial, right? So t is not an exponent now. The exponent is kappa, so it goes down. And for example, in Guillaume's note, the pseudo-marginal MCMC algorithm is in that class and not that class. So there are some useful algorithms that are polynomially ergodic, but in a lot of generality, algorithms tend to be geometrically ergodic. So Langevin, Hamiltonian Monte Carlo, when they are ergodic, they are geometrically ergodic. Okay, mixing time. So usually people talk about mixing times to say the time it takes for the distance to be specified to become less than epsilon. The epsilon mixing time. So sometimes the results are phrased in terms of rates or sometimes in terms of mixing time. Mixing time is more concretely how many steps you need to be doing. So typically we have upper bounds on the rates, and so we also have upper bounds on the mixing times. There are some rare lower bounds in the literature, like in order to approximate this target with this algorithm or this class of algorithms, you need to do at least this many steps, but that's also quite rare. It started to happen with some gradient-based MCMC and simple classes of functions like strongly log concave in the last 5 years. Okay, so going back to, moving on to how we're going to obtain those rates. We're going to use couplings. So there are many types of proofs for rates of convergence, and here we're going to focus on one family of techniques under the umbrella of couplings. But taking a step back from Markov chains, if you just have two static distributions, P and Q, what is a coupling? It's just a joint distribution that has marginals P and Q. It's just a name for a joint distribution that has given marginals. So maybe you're familiar with the concept of copula. A copula is a joint distribution typically that has uniform marginals. So this is a joint distribution that has just a given, prescribed marginals P and Q. So if you integrate the second argument, you get P. If you integrate the first argument, you get Q. And the TV, the total variation distance between P and Q, has many representations, so many definitions. They're all equivalent. You can prove one from another. It's either the maximal difference of the probabilities assigned by those two distributions to all sets. So this is a sum over the sets. Or if you have densities, to me, one of the most intuitive definition is the one with densities. If you have two densities, you can look at the difference between the two as the integral of the area in between. And if you divide that by 2, you have a quantity between 0 and 1. And that's exactly the same as the first definition. The first definition is much more general. You don't need densities. If you have densities, you can also rewrite this as that. So you're saying that this is 1 minus the area under both curves, so the pointwise minimum. Because, of course, the distribution integrates to 1, so there's a relationship between the area of the difference and the area under. So you can prove that. And then the final representation is useful for us, is the so-called coupling representation. And so it's the infimum of all couplings. So all joint distribution with such that X follows P and Y follows Q. There's always one because there's an independent coupling. where x and y are independent. So there's a set of couplings with at least one element. But if you take the infimum of all couplings, of the probability that x would be different from y. Okay? So if, for example, the distributions are continuous, and you take them independently, the two variables, then the probability that x is different from y is equal to 1. And so what this says is that, in fact, there's another coupling. There are multiple other couplings, typically, that give you a quantity less than 1 for this. So which is quite something that I find quite surprising, or not usually taught. So if you have independent continuous variables, we know that they cannot be exactly equal. But actually, if they're not independent, they can be dependent in lots of ways. And there are ways that make this less than 1. So that means there's a non-zero probability that x could be exactly equal to y, while both following their prescribed distributions. So tomorrow, I'll give you lots of examples of this and algorithms to generate those couplings. So there's other definitions of distances that also involve couplings. And one of the big family is the so-called Monte-Kantorovich or Wasserstein distance. So here of order k between p and q. That can be defined as an infimum over all couplings of the expected distance to the power k between x and y. So in fact, if you're taking the 0, 1 distance, you retrieve the TV. The TV, in a sense, is a particular case with the 0, 1 distance, but here you could have the Euclidean distance, for example. So there are lots of interesting special cases. So if you're in one dimension, this is an integrated distance between the quantile functions. Okay, so here we saw TV as an integrated distance between densities. But in fact, if you could also compare the CDFs or the inverse CDFs, the quantiles, and get other distances. So if you take the one Wasserstein distance in one dimension, it's also equivalent to integrating between the CDFs. But I think maybe I'm wrong, but I think in general order k, still one dimension, you have this representation. And there are other representations. So for example, in the one Wasserstein is also the sup over all Lipschitz functions with coefficient 1 of the difference of expectations. There are other distances as well that generally are called integral probability metrics that are defined in terms of the sup over a class of function of difference of expectations under the two distributions. So here we're going to look at this type of distances. And we're going to go back to Markov chains now. So the very great idea of obtaining rates of convergence from couplings of Markov chain, that's an old idea. I'm going to explain the basic, and then I'm going to introduce a toy example in which we can really work out the rate of convergence. It's going to be a very, very toy example, nothing like even a probit regression. Much simpler, but we can work out exactly the convergence rates. And so the ideas here really date to Dublin, Wolfgang Dublin, in the 1920s. Okay. So Markov chains existed already, and the question was how to prove convergence rates for the Markov chains. And the idea of Dublin is is interested in xt, going to a stationary distribution. And artificially, he introduces another process, yt, which is also a Markov chain, which transition kernel is the same, but this one is already at stationarity. So we can't, in MCMC settings, this is a fiction, right? This is a fiction. This is a theoretical device. We can't sample from it, but theoretically, we imagine that there's the Markov chain we're trying to analyze that goes to stationarity, and there's another one that's already at stationarity. And the idea of coupling is basically to make them coincide, to look at the time it takes for them to coincide, and that's going to give us the time it takes to reach stationarity. That's the idea. So again, we introduce a second process already at stationarity, and we try to make them coincide. And so we imagine that we can make them coincide at time tau, call that the meeting time. So suppose that there is a time tau such that after that time, they're together. So for example, the trajectories could look like this. So it may seem quite difficult to generate this in MCMC settings. We're going to try to do that tomorrow, okay? Or after tomorrow. We have 2 more sessions. But it turns out we can do that for the algorithm that we've been talking about.
So this is assuming that the kernel is pi invariant, right? Because
Yeah.
Otherwise, you could not have the YT distributed to pi for all t.
Forever, yes. You're right, yeah. If you want them to stay forever together, they need to be at least going to the same distribution. And so if that's satisfied, so if you have a construction like this, so the TV between pi t and pi is the TV between the law of xt and the law of yt, because yt is distributed according to pi. And remember the coupling representation of TV. TV is an infimum over all couplings of this quantity. So for any particular coupling, you get an upper bound. And so the upper bound is probability that xt is different from yt. And that means that the meeting has not yet happened. So that event is the same as the meeting occurs later. So you have an upper bound on the quantity of interest here, the distance to stationarity, in terms of the survival probability of the meeting time. Or 1 minus its CDF. So then it's a question of analyzing that meeting time. It turns out to be much easier than the original problem in many cases. So, yeah.
So this meeting time, just to make sure I follow, we are, as a theoretical device, constructing this joint process. And we're trying to understand what are the decisions we have to make to construct this joint process. And
Right.
that influences a certain variable. So we have pi as our target distribution.
Right.
We have transition probability kernel P.
Right.
That we know is pi invariant.
Mm-hmm.
And then we also need to decide the joint relationship between xt and yt for all of our t. And
Exactly.
so when we say that, so there's a joint relationship between xt and yt, and p is also relating the joint relationship between that vector at time t and time t plus 1.
Right.
And so when we're saying we need to construct in
Yes.
such a way that they meet and then follow forever, is that putting, so that I would imagine that would put restrictions on any contemporaneous vector, so the relationship between xt and yt, but does that also place restrictions on which kernels we can consider so that they can marginally move in the same way after t?
Yes, so that's a very great question. Like what is already an input of the problem and fixed, and what is the leeway here? What's the degree of freedom? So indeed, the degree of freedom is how correlated those 2 processes are going to be, because marginally they need to be following P. That's already decided. So marginally, I mean, if you just look at the xt, it starts from pi 0 and it propagates according to P. Yt starts at pi, propagates according to P, so that's already decided. And so what can we do? There's still some degree of freedom, because indeed there's all the relationship between the x's and the y's at the same or different times, basically. In fact, we're going to restrict ourselves to a subclass that's going to be much easier to work with, where xtyt itself is a Markov chain, which is not, we don't have to do that, but it's going to be easier. And so by restricting ourselves, we're going to have a loser bound, potentially. But then the only thing we have to decide is how xt plus 1, yt plus 1 is drawn given xtyt. So the transition of the coupled chain. So that's what we're going to basically define, but we'll have to satisfy the 2 marginal conditions. So thanks for this comment. So that's for TV. So for TV, we need the chains to meet, because the TV representation involves this probability of variables being different. But for Wasserstein, it's different. So we can do the same business in Wasserstein distances. And then, for example, make things simpler with the Wasserstein 1, so we don't have this k. It's an infimum over all couplings of the distance, expected distance between xt and yt. And if you take any particular coupling, then you have an upper bound. So now you don't need the chains to meet necessarily, but in order to get a good bound, a bound in particular that goes to 0 when t goes to infinity, you want the expected distance between the chains to go to 0. So you'd like to construct chains that sort of contract without necessarily becoming exactly identical. And again, this is a theoretical construction. We can't sample from pi in MCMC setup. This is just to prove convergence rates. Yeah.
So you just mentioned that this second component, this YT, that's just to help us in theory. I'm wondering if we were to think of something more along the lines of like a Cauchy sequence where we have like XT and YT will both eventually marginally go to pi. And we want to see how like these two chains would end up stabilizing, and the hope is that they would stabilize at pi. Maybe would there be any sort of practical use of this chain, not just for like theoretical purposes, but would that also help us figure out what this meeting time might be, or
Yeah, so because you don't want to assume a pi stationary chain, but you prefer to have two chains that are neither of which is stationary.
right? But eventually will become stationary when you pass them through this.
Right. I don't know if it would help in the theory, but that's basically what we're going to do in practice because we won't be able to sample from pi. Otherwise, we wouldn't be doing MCMC, right? Probably. Although there are cases, because it could be that you can sample from pi, but it's very expensive, so you can do it once, but not many times. There's all sorts of cases, but in the theory, I don't know if it would help, although you could imagine that, with the triangular inequality, you can upper bound this by something that relates to the two different chains, but I'm not aware of cases where it helps. I mean, in theory, we're allowed to dream and to imagine that the chain is stationary, so why not doing it, right? But in practice, that's exactly what we're going to do. Okay, yeah. I want to talk about the donkey, though. But I want to talk about the donkey.
So I guess that's where we need them to be drawn from pi. I thought we just need them to have the right kernel, and then it's the time until they touch wherever they start from. But
Yeah, so really here I'm just talking about the theory, how couplings is used to obtain convergence rates. And here it's important that YT follows pi because we're looking at the distance between pi t and pi. And so if we want to say that that's the law of xt and that's the law of YT, right? By the construction here is that YT follows pi.
But if I know I'm going, if I know the chain's going to pi eventually, and I want to get my bound, and I start from any 2 points,
Right.
eventually they touch, so it doesn't matter where I start, and it must be that I'm at stationarity.
Right.
So I never had to have anything drawn from pi. I just get it.
Yeah, you're right actually because you can do some. You could say, maybe that's what you have in mind. You could say that pi t minus pi is less than in TV or in any distance that satisfies the triangle inequality than pi of x. So to make things simpler, I'm going to assume that we start in a Dirac mass at little z for x. And then I have something like this. I think. And so then if you have a bound on this and you can integrate that bound with respect to pi, indeed, you can only think about a chain starting from z and a chain starting from x. So that's what you mean.
Yeah. Intuitively, the coupling story goes through too.
Yeah, you're right. Yeah.
If anything starts after some time, it doesn't matter where it came from, so that must be stationary.
Yeah, I agree. Yeah, so it's a triangular inequality thing, but you're just losing something when you, again, for the theory, there's no massive benefit, right? You're just losing a bit of the sharpness. Well, this is not sharp anyway, right? Because it's interesting to talk about the sharp case. It's called the maximal coupling. But okay, so I want to talk about the donkey. So this is a very simple Markov chain. It's called the donkey walk. I didn't make it up. So it's one of the classics. And it's the story of the Buridan's donkey. So it's a donkey that wants to drink water, but also to eat some hay. And can't decide, so it steps on the left, steps on the right, and never reaches either. So the model here is that we're going to take a uniform step on the left, and then followed by a uniform step on the right. Right? So from this position, denoted by zt minus 1, we take a step to the left by sampling ut with this arrow to the left, multiplying by this quantity, we get a number on the left, uniformly. And then we draw another UT arrow to the right, to sample uniformly in that region. So that's what this second equation is doing. Okay, so this Markov chain is just zigzagging with random steps. You can combine the two steps to express the new position as, so this variable times the previous position plus that variable again. Okay, so the question is so is there an invariant distribution? So you can work out an invariant distribution for this. It's actually a beta distribution. And you may wonder what's the rate of convergence to that limiting distribution. So here's the coupling. So we're going to employ the technique we've just seen. We imagine our donkey, started from any arbitrary distribution. This is the stationary donkey with a tilde. And the two donkeys are going to evolve, not independently, but using the same variables at every step. So the same realization of the variable at every step. And then it's very easy to look at the difference between the two. Right? So the difference between the two at time t, one minus the other, it's the same quantity that multiplies the difference at the previous step. This added variable disappears when you subtract. You subtract the second line from the first line. And then if you look at the expected distance, you find that the expected distance at time t, so I'm going to call it delta t, is equal to the expectation of ut left 1 minus ut right times the distance at the previous time. Okay? And so, of course, the expectation of the product of two uniform, that's pretty reasonable. So that's 1/4. Right? They're independent. They're independent of the previous location as well. So we basically get that we get an expected distance discounted by the factor 4 at every time. So recursively, we obtain the rate of convergence in Wasserstein 1. It's 1/4. Okay, so it's converging geometrically with rate 1/4. Super precise here. Right? And what do we get here? We get the initial distance. So here we can bound the initial distance by 1 because the donkeys live in 0, 1. So we get the most precise convergence result ever. Right? So if we have this, we know exactly what t we could choose in order to have the distance less than any epsilon. So that's the dream. Right? In MCMC, it will never be as precise. But if it was precise, then... And there are all sorts of methods now trying to leverage machine learning and simulations of the Markov chains, many simulations and machine learning to try to obtain like estimates of rates. Because if you had like precise quantitative estimates, then you could say, I want to be 0.01 away in TV. This is my number of steps that brings me there. So it's very rare. There are some people like Jeff Rosenthal in Toronto, for example, who has actually managed to obtain precise convergence rate in simple but not completely trivial setup, like really statistical setups, like some Bayesian regression with some actual data. And he managed to get that the bound is 10 to the 7 times 0.999995 to the power t, or something like that.
With coupling arguments?
No, actually with all sorts of combination of clever tricks, which is completely different from one example to the next. So it's very skillful. But it's not typically using coupling arguments. Okay, so this is a very simple example. It turns out nearly the same reasoning works for what looks a bit more complicated, the Langevin diffusion, and its discretization, which is called the unadjusted Langevin algorithm. So if you look at the Langevin diffusion, we've seen it yesterday a little bit. So we have a deterministic drift with a potential function u, and it goes towards the distribution with density proportional to exponential minus u. And there's this Brownian motion term on the right. And so we're going to do exactly the same trick as before. We're going to introduce a stationary version of the process, y, and we're going to drive the two processors with the same noise. Like the same idea that before we used the same uniforms for the two donkeys, and here we use the same Brownian motion for the two Langevin diffusions. And that's really convenient because you imagine if you have the two diffusions, you do one minus the other, the Brownian motion completely disappears. And so the distance, the evolution of the difference is completely deterministic. Yeah? So you have this differential equation that tells you that basically they're going to go closer to one another. So why would they go closer to one another? Well, you need assumptions, in fact, but if U is strongly convex, then when you differentiate the square difference, which of course is important because we're thinking about Euclidean distances. So if you do this quantity, you obtain that form. And by definition, if U is strongly convex, this means that this is less than the right-hand side here. Okay, I don't know if this is like convex, some convex arguments. So if you have a convex function, it means that at every point it's higher than a derivative, a tangent line right here. But if it's strongly convex, it means that you can also squeeze in a quadratic function. Yeah. There's a quadratic function, so this one is the form ax squared plus bx plus c. This one is gamma x plus delta. And so strongly convex means that the function can be lower bounded by a quadratic function like this everywhere. So it gives you this kind of inequality. And then, so what you get from there is you can apply Grunwald's lemma to say that if the derivative of the function f, which here is the squared distance between the two chains, is less than Cf of t, then the solution of the differential equation will be less than the solution that you would get if you had the equality. And if you had the equality, it would be simple to solve. You get the exponential convergence. So it's called Grunwald's lemma. So from this reasoning, you find that the expected distance at time t square is less than exponential minus 2kt times the constant, where k is the strong convexity constant. So then if you assume on top of that those initial conditions have finite second moments, then you get geometric ergodicity for the Langevin diffusion. So this is a very simple proof compared to other types of proof techniques for the convergence rates of processes. And it works the same way for Euler, so the discrete version of this Langevin diffusion. You have a step size epsilon. So you follow the gradient and you add some Gaussian noise. You drive two chains with the same noise. So you look at the difference, the noise cancel out. You have some sort of deterministic, discretized version of the previous equation. And in Appendix A of Wisi-Bono 2018, you'll find this reasoning that leads to, here assuming L smoothness and K strong convexity, that you find the rate of convergence in this form. Yes. So this is just one step, but you do it t steps and you have t to the power t. You have this to the power t. So here, again, this is very quantitative. We know that the rate of convergence depends explicitly on the K constant, the L constant. So that has been the sort of one of the exciting developments in the theory of MCMC in the last, say, 10 years is really the obtention of very explicit rates that depend on the critical aspects of the problem. For example, this does not depend directly on the dimension. So maybe your conditioning number and smoothness will depend on the dimension, depending on your type of models, but here it just depends on the so-called conditioning numbers, the properties of this smoothness.
What's the square? How much can it terms off? Like, what kind of square is it?
Here?
Yeah.
Sorry, it's the second derivative.
Oh.
It's the Hessian.
No, like not the gradient, the bound. So like you take the square of the difference
Yeah.
So
It's
what's the square, like in understand in terms of, like is it L to norm or something?
yeah. It's basically the square L2 norm. So ultimately we want to control the Wasserstein distance, which is expressed as an infimum over the expected distance to the power 2, because here we're looking at the 2 Wasserstein distance. Again, out of convenience. Yeah. So that's why some of the papers, they use the 1 Wasserstein, some use the second Wasserstein, and sometimes you can't compare easily the results because it's purely chosen for convenience. Okay, and the same reasoning works for Hamiltonian Monte Carlo. So for example, you have this figure in Mangubi and Smith, 2 Hamiltonian Monte Carlo trajectories. One starts at x1, the other one at y1. And you see what happens is that they always are given the same velocities. So P1 is the same. The trajectories, of course, are different. And you see that they end up at points that are closer from one another than the points that were started. And again, they're given the same P2, and they end up here and here. And this is quite sophisticated, right? Because, I mean, who knew that if you give the same velocity to 2 points and they evolved according to the Hamiltonian dynamics, they would end up closer than when they started, right? So it's only true under some conditions and for certain integration times and so on, but it's remarkable. Like, so in strong log concave targets, if the integration time is not too long, this happens. Contraction at every step. And again, this is a way of obtaining a mixing times. So I wanted to flash this table, not to go into the details, but just to give you a sense of what you could find in papers on the theory of MCMC these days. I'm going to zoom in maybe a little bit. So you find different algorithms. Here, HMC, for example, different conditions on the initialization. Different assumptions. So product distribution means the target distribution is just made of independent components. It's a very strong condition. Hessian is Lipschitz, and so on. And then what you get here is the number of gradient evaluations. So that's the number of, it's kind of a proxy for the number of steps, if you want, but in Hamiltonian Monte Carlo, because you have this Hamiltonian integration, you do more than 1 gradient evaluation per step. So this is counting directly the gradient evaluation in the idea that this is the expensive part of the algorithm. This is the part of the algorithm that depends on the data set. If you have a big data set, it costs more. And it gives you the number of gradient evaluation for what? To be at epsilon away from stationarity in some metric. And so what they would compare basically is those numbers, the rates of how this depends on D, the dimension. Kappa would be the so-called condition number. So that's the L smooth constant divided by the M strong convexity constant. And there's no consensus yet. There's rarely a lower bound that tells us what's the best thing we could do. But at least we can compare upper bounds. And in the last 10 years, it got incredibly sharper than before. I mean, there was nothing really before. So that's one of the exciting developments. That's not really my expertise, in fact, but I wanted to convey still this kind of exciting developments because even though it concerns still very sort of toy examples or fairly simple classes of distributions, but it gives you hope that someday there will be results like this for realistic MCMC problems. And some of those techniques are based on couplings, some of them are based on completely different techniques. Some of those results. Yeah, it's a good, so here it's saying summary of epsilon mixing time in TV distance. So here would be the TV distance. Okay, so I'm going to skip this bit on Langevin diffusion as itself a gradient descent algorithm on the space of measures. And just to announce what's coming next. So here we looked at the bit of theory of MCMC, coupling, Poisson equation, CLTs, rates of convergence. But again, typically it falls short of giving you exactly how many steps. Like in the probit regression example, again, we look at those traces. We see this theoretical literature that doesn't quite apply. So that doesn't directly help us. So here's the paper by Rosenthal where there's very explicit rates for certain MCMC algorithm, but it's very rare. And so, but in practice, every single practitioner needs to choose a number of steps. You can't do MCMC without choosing the number of steps, or letting it run until it stops. And your stopping criterion may just be the time at which you're fed up with it, but ideally there be something a bit more principled. And so we're going to try to look at methodology next. So we revisit couplings and Poisson equation, but with a view towards implementing it and to really concretely address those questions. Thank you.
The Poisson equation trick, do you have the sense that it could be used as a trick for giving CLT elsewhere?
Yes, that's a good point. If it's not a Markov chain, you mean outside of Markov chains?
Yeah.
Yeah, it's possible that there are some stuff like that. I think it's used a lot in analysis of Markov decision processes, in fact, for example. So there are, which have a Markov chain component in it, but it's more sophisticated. It's less homogeneous, and this still works.
Okay, thank you, Pierre.
Thanks.